Today I'll be talking about helium-3 and the lunar vacuum, framing a $17 trillion opportunity. I want to thank the committee for allowing me to present at AVS International today. There's a lot of reasons to be at your committee talking about helium-3. Here's just a few of those, specifically and including vacuum. The singular focus of our company, Lunar Helium-3 Mining, is to extract helium-3 from the surface of the moon to provide it for existing uses, which we will talk about, and in particular, upcoming future nuclear fusion reactors, which is the world's first true green energy at volume, and also for future quantum computing. Those would be the three reasons to provide helium-3 off the surface of the moon for Earth. My background is a little eclectic. I specifically want to point out the fact that I learned about helium-3 when studying planetary geology. Okay, our agenda is going to be fairly action-packed. It's going to include why go back to the moon, where do you get helium-3 from, the use cases we'll dive into detail, revenue projections because it's very expensive to go to the moon, and then some difficulties and challenges with extracting helium-3 from the surface of the moon. So why are we going back to the moon? Most space endeavors are for scientific research, and that's a cost center. There's no revenue that's generated from that. Or in this case, going to the moon again could be for scientific research. It could be for global competition. We are in somewhat of a space race with China for the second set of humans going back to the moon. Obviously, Apollo was the first, or potentially to prepare for a Mars mission. I will offer the alternative that we could be going to the moon as a revenue generator, not a cost center. And helium-3 is the only resource on the surface of the moon, as you will see, that makes sense to create a positive return on investment. There's no other resource on the surface of the moon that can accomplish that. So what is helium-3? It's an isotope of helium. It has two protons, one neutron. It's non-radioactive. But the most important thing is it has very special use cases on Earth. Presently, helium-3 on Earth has been sourced from weapons productions from using tritium. So it's a byproduct of nuclear weapons production, specifically in the Cold War era, using the decay of tritium. The estimated US supply is significantly less than 10 kilos. That's it. And all the United States, it probably is lower than 5. Helium-3 also comes from the sun. It travels with the solar wind, and on Earth, it's captured by our atmosphere, so it never really makes it to the ground. On the moon, there's no atmosphere, so helium-3 has been baked into the lunar regolith over billions of years. It's estimated that there's more than 1 million tons of helium-3 on the surface of the moon. If those are even close to being accurate, that could fuel nuclear fusion for hundreds of years. The bad news is the concentration is about 1 to 15 parts per billion. There's a lot of hypothesis on why and how helium-3 is in the ground called regolith. Probably the most important point is that helium-3 again comes from the sun. It gets embedded in the very top layer of the regolith with loosely bound connections, such as van der Waals forces. Okay, there are present use cases of helium-3 on Earth. This is a table of, in the left-hand column, present use cases with border detection using radiation as the most important application of helium-3. In the right two columns, it's important to point out the dwindling supply. If you look in 2008, the next to last column to the right, the total usage in that 15 years ago, or whatever it was, 15, 16 years ago, was about a kilogram. As the supply has dwindled since then, the amount of usage of helium-3 has gone down dramatically. In fact, it's down so low that it's difficult, if not impossible, to have enough helium-3 for radiation for border detection. Now, the big drivers of helium-3 are going to be the next two use cases. The first is going to be nuclear fusion, not to be confused with nuclear fission. Here's a fun question. If you drive an electric car, been on an electric train, the question is, are you driving a green vehicle? Chances are you're not. Depends on where the electricity is coming from. Because the present source of electricity across the globe is roughly 70 to 80% from burning fossil fuels or from nuclear fission. Some highlights of the problems there. The world burns about a little over 9 billion tons of coal per year to produce electricity. That does produce a significant amount of CO2. In fact, it's estimated that the amount of CO2 produced per year could fill 10 million Olympic-sized swimming pools. On the fission side, we've had catastrophic explosions such as Chernobyl, in which the surrounding area around Chernobyl is going to be a no-use case, can't go there for 200 to 300 years. And whoever talked about storage of radioactive waste for up to 100 years? There's no system in the United States to do that. So the good news is the future source of electricity could come from nuclear fusion, again, not fission. Fusion is when two or more atomic nuclei combine or fuse, and they release more energy than is put in. When they release more energy than is put in, that's the Holy Grail, and that's what they are trying to achieve and have achieved. There are two main reactions to be aware of. That is deuterium and tritium. And in that case, you're going to get a helium-4, a neutron plus energy. We have coined that reaction nuclear fusion 1.0. If you had helium-3, you'd rather use that. That would be a reaction between deuterium and helium-3. That would create helium-4 also, this time a proton energy, and we've called that nuclear diffusion 2.0. In the next slide, I'll show you the differences between these a little bit more. One big pro of nuclear fusion, whether it's with tritium or helium, and a big one is it cannot explode. And nuclear fusion 1.0 is right around the corner. In fact, there is a contract between Helion Energy and Microsoft for fusion technology. It is predicted over the next 10 or 20 years, nuclear fusion will begin to replace nuclear fission and the burning of fossil fuels. Now, the dirty little secret is nuclear fusion 1.0 with tritium is not green. First off, there's no obvious, easy way to scale up the production of helium-3. I'm sorry, of tritium. Tritium comes from, first off, lithium in the ground. It has to be mined out of the ground like any other product out of the ground, then converted to tritium through a fission type of a reaction. It's not really known how to scale it up well. It has the problem that you have to store byproducts for up to 100 years. Because it kicks out a neutron, it's more dangerous for the human and the reactor itself. If you had helium-3, which would be nuclear fusion 2.0, it's scalable by bringing back more helium-3 from the surface of the moon. There's no byproducts to store. And it kicks out a proton, not a neutron, which makes it safer for the human and the reactor. The bottom line here is if fusion is done with helium-3, it's going to be the world's first green scalable energy source. Nuclear fusion 1.0, or fusion in general, has been under development for a number of years to a tune of more than $6 billion in more than 10 countries. So it's advancing, but it's mainly with tritium. On the opposite side, the discussion of using helium-3 or mining helium throughout the surface of the moon is more in its infancy. Let's talk about some big picture numbers. If you had fusion across the entire globe producing electricity and you used helium-3 as the fuel source, if you do the math, you're going to end up with a need of about 570 metric tons of helium-3 per year from the surface of the moon. from a volume point of view, let alone a green energy point of view, if you did this with coal instead, you'd need about 9 or more billion tons of coal to produce the same amount of electricity. Let's go on to our next use case, and that's the use case of quantum computing and helium-3. And I'm not an expert by far in quantum computing, so keep that in mind. Quantum computing, while still experimental, is advancing rapidly, and I love the comparison here. If you took a string of numbers that was 2048 in length, and you try to factor it or break it down into its prime components, that complex process would take about 10,000 years with the classical computer, but less than a half a day with the quantum computer. Imagine the applications from cryptography to drug discovery to potentially curing cancer. Now, what does that have to do with helium-3? You need helium-3 to cool a quantum computer down to 0.01 Kelvin so the qubits could function correctly. Without cooling it to this temperature, there's significant error rates. Now, each quantum computer uses roughly 1 to 10 liters of liquid helium-3 for cooling, along with helium-4, in something called a dilutional refrigeration setup. Again, without helium-3, you cannot cool it down to 0.01. Now, no one has actually estimated how many quantum computers there might be, but we actually took a stab at that just for arithmetic here. We made an estimate that there might be 10,000 quantum computers in 15 years. If that was the case, you would need about 4 metric tons of helium-3 for those 10,000 quantum computers. There's significant strategic security issues here. Whoever has quantum computing, whichever country has or set of countries, may have an advantage in AI encryption and cyber warfare. So it's important that the United States and its allies obtain helium-3 before other actors do. From a revenue point of view, it's important to look at this because it's very costly to go to the moon. Today's helium-3 prices are about $30,000 a gram or $30 billion per metric ton. Ironically, that's less than the cost of tritium. And that price will probably go up and down with market conditions. I suspect it will go higher when we bring on quantum computing, but probably lower when we need to do this for nuclear fusion to produce electricity. If you use today's dollar amounts, and again, we need about 570 metric tons of helium-3 for nuclear fusion. That's about $17 trillion worth of revenue per year. On the quantum computing side, you would need about 4 metric tons, as we discussed, and that's about $119 billion. Let's shift gears and talk about some of the difficulties of extracting of helium-3. And before we do that, let's look at the competitive landscape. We are not the only entity talking about the extraction of helium-3. In fact, China has actually returned samples recently back from the moon, has declared they want to go to the moon to extract helium-3. And my interpretation of that is they are going to go to the moon to extract helium-3 initially for quantum computing for strategic dominance. India, who's farther behind in its space program but gathering steam, has also expressed going to the moon to extract helium-3. The United States has no public position on this. We are running around the United States giving talks to policy conferences, fusion conferences, quantum conferences, green energy conferences, and space conferences talking about this to try to get the United States to look at helium-3 as a strategic initiative. There are other private companies looking at the extraction of helium-3 from the surface of the moon. Our company's approach, and we think we have a competitive advantage, is we are looking at the extraction using moon-based techniques to extract helium-3 as opposed to Earth-based techniques. We're going to get into that further. This is a very important slide. These 3 things need to come together in order for there to be a positive return on investment for helium-3 extraction to bring back to Earth. Number 1 is the reduction in transportation costs to the moon has to drop probably in proportion to the drop we've seen with putting satellites up in low Earth orbit. Second is commercialization of fusion. That'll be the volume driver of helium-3 needs. And third, to the bottom right in red for a reason, is using lunar-based extraction techniques and not Earth-based mining techniques. Is this the future of lunar helium-3 mining? Most people would laugh at that and say, no, this is a gold mine in Australia, but the principles of extraction from a mining point of view are the same. You would blast or grind up the ground to extract your ore. You would then chemically or heat process the ore to extract your resource. In this case, it's gold. You dump out the back end of the processing, your tailings, the wasted rock, and you hold on to your precious resource. So keep that in mind. That's the typical way resources are extracted on Earth. Now, this looks like nothing like an Earth-based process. This is a schematic of a potential way of extracting resources off the surface of the moon. I would argue this device uses the same Earth-based processes. In the front, there's a bucket wheel, that round wheel that requires a lot of energy to grind the ground. And then the material or the ore is transported via a conveyor belt inside this device in which heat or chemicals are used to extract whatever resource you want, and out the back you dump the tailings. So this has a lot of energy of extraction and a lot of moving parts. So keep that in mind as we talk about the extraction of helium throughout the surface of the moon. So with that in mind, let's talk about some challenges of extraction. I'm only going to go over 4 at a high level, but there's plenty more. The first problem is the extreme low concentration. The good news is, again, there's about an estimated 1 million tons of helium-3. However, it's in very low concentrations. So you cannot go to the surface of the moon and use an Earth-based mining technique, because Earth-based mining techniques are based on the extraction process in which there's a much higher concentration. For example, a copper mine has about 0.5 parts per 100. If you use that exact same process on the moon, you roughly would extract 1 part of usable helium-3 from 999 million unusable parts of tailings. You dump those out the back end. The energy cost of this extraction method is just not practical or doable. Consequently, our company has come up with a very low energy extraction process designed for lunar conditions. Another challenge is the dust. The regolith, which is the ground, the dust, if you look at the dust underneath a microscope, it's sharp and spickly. That's because there's never been water or wind on the surface of the moon to soften or smoothen the dust. It's 45% silica. It's charged from solar radiation, so it could levitate above the ground. And there's a fair amount of iron associated with this dust. This makes this dust very clingy and exceptionally abrasive. 50 years ago, approximately, Gene Cernan on Apollo 17 said, I think we can overcome other physiologic or physical and mechanical problems except dust. He was trying to tell us 50 years ago that we need to start planning for going to the moon. And one of the biggest hurdles, if not the biggest hurdle, will be the extraction or the use of movement or any types of effort on the moon, because dust is going to get in the way of everything. There's another slide about the dust. Let's look at Apollo 17, Gene Cernan's flight. There were 2 astronauts on board, and they spent about 22 hours on the surface walking around doing EVAs. During that very short period of time on the ground, the dust destroyed vacuum seals. It eroded through 3 out of 12 to 15 layers of Harrison Schmidt's boot, and it covered and compromised many things. So our solution to this is to use the least amount of moving parts, because if you have a device or a system that has a lot of moving parts, it's going to fail. The next is the lunar environment is a vacuum. We're going to talk about that in a couple slides, but underneath our rover is where the mining process takes place, and we want the ground in which the ground is heated, when the helium-3 comes out of the ground, we don't want that going shooting off into space. Consequently, you're going to see coming up a skirt around our rover. We want to minimize the skirt being disrupted as it rolls across the ground. So when possible, we would like to have loose rocks go around and behind our rover and not underneath it. Now, if we used a regular plow, we would end up pushing the rocks into the next up and coming lane because the rover would go up and down and up and down. We devised a very clever little system. Let's look at this again on the next slide, in which loose rocks would hit the bidirectional plow in the front. They would be directed around the rover. Point number two is there is a containment system to keep them from going laterally or to the sides. These rocks are then directed behind the rover where point number three is. So you're basically, if this works correctly, many of the loose rocks are going to go around and behind the rover to minimize disruption of the skirt, which we're going to show on the next slide, or the next slide's coming up. So again, for context, Earth has obviously one atmosphere of pressure. The moon has none. If you release gases out of the ground, let's say you heated the ground on Earth and gases came out of the ground, they're going to be fairly slowed by atmospheric pressure. Whereas on the moon, these are going to go shooting off at ballistic speeds into the atmosphere unless they are contained. So our solution was a novel, simple containment system. And I've hinted at it, and here it is here. You can see this in blue. It's a malleable or flexible skirt, for lack of a better word. It goes all the way around all four sides of the rover that could be moved and go over rocks. The idea is to capture as much of this volatiles as they go up into the air underneath the rover and not escape out into the atmosphere. Our company was designed a couple of years ago with the intent of working with the moon and not against it. We try to identify the moon and its environment and try to work within the environment of the moon. Again, not against it. Our team has diverse backgrounds. We collaborate. We try to understand the lunar environment as much as possible. Ultimately, we don't want to go to the moon with Earth-based extraction techniques. It will fail. We are attempting to go to the moon with lunar-based extraction techniques. Our company has a number of issued and pending patents. And I like this slide because it kind of summarizes our focus. If you look at the graphic, there are 5 steps from identifying helium-3 concentration at the surface and subsurface, different methods of heating the ground, then directing the volatiles, which is the gases that come out of the ground, separating them, and eventually taking the helium-3 gas and compressing it down into liquid form, which would be the form that you would use to transport it back to Earth. So in summary, there's an estimated 1 million tons of helium-3 on the surface of the moon. We're going to need that for fusion 2.0, which will be the only green scalable energy source that we know of. That's a $17 trillion a year industry in today's dollars. It's also going to be for strategic national security to spin up and cool down quantum computers. As I mentioned earlier, the success of a positive return on investment eventually will be when transport to the moon comes down in cost, fusion comes online, and we switch over to helium-3, and we adopt lunar extraction techniques, not Earth. Our company is singularly focused on this undertaking, and if you look at the last bullet point, we believe that helium-3 extraction is the tip of the sphere for a lunar economy. It's going to take numerous companies and countries to work together for this industry. With that, I thank you for your time. If you'd like more information about our company, please visit us at lh3m.com.